All right, so far we explored how scale factor affect our dimensions in an object. So if we have the original and the new, we just know that to make the new one, we change every single dimension by the same amount. It's called the scale factor, okay? So I want you to think of, right, this is the original and we're making a new shape. So if this is my length, this is the width, and this is the height of the original, now we're going to make a new shape, right? So let's imagine if we were to multiply the height of this one by 2, because we're imagining we're using a scale factor of 2. We're doubling in size. So we're going to go multiply this by 2, okay, times 2 to get 6 centimeters. We're going to multiply this times 2, so the width, to get 4 centimeters. And we're going to multiply the length times 2 to get 10 centimeters. So our new box measures 10 by 4 by 6. Okay, that's what happens when we use a scale factor. Okay. But I want you to think in broader terms. If k is equal to 2, in this case, to go from the 3 here to the new dimension, I basically went k times 3. I want you to put this in brackets. To get from the 2 to this new dimension, I went what? K times whatever this was, 2. And to go from the 5 to the 10, I went k times 5. And we're going to highlight this. Okay, we're going to highlight those little brackets that I just talked about there. So everything was doubled, right? Note I could have had k is equal to 3. If k had been 3, we would have multiplied everything by 3, and so affecting it differently, okay? So let's look at our, we did A already. We figured out the dimensions of the new prism. Now we're going to talk about the surface area, okay? So we're going to do surface area of the original is going to be, if we use this formula right here, okay, it's going to be 2 times length times width plus 2 times length times height plus 2 times width times height, so width and height. If we look at the surface area of the new box we just made, I want you to now not focus so much on the 10, 4, and 6.
Unity, Goodmanson, can you please return to room 61?
We would go 2 times length. Our length, I'm going to use k times 5. So k5. We'll just go k5 at this point. Times, what is the width here? The width is k times 2. I know it's 4 as numerically, but we went scale factor times 2. So we're going to go K2 plus 2 times length times height. Our length is K5 times our height is K3 plus 2 times width times height. So our width is K2 and our height is K3. Whoa, what are you doing there, Mr. Dirksen? That looks very weird and ugly. Yeah, so what I want you to notice that for us to do our new shape, K affected every single, look at that, there used to be a 5 and a 2, but now the 5 and the 2 have been affected by K, each of them, right? When we make the 5 and the 3 is still here, but for the new shape, both the length and the height have been affected by K, and so forth. So everything has been affected by a factor of K. So let's clean this up a little bit. This is still surface area of new. I want you to see something here. We're going to do 2 times. If I went K times K, what is K times K? K squared, right? KK, that's K squared. And then it's times 5 times 2 plus, let's clean this other one up. K times K is K squared times 5 times 3 plus 2 times K and K multiply again times 2 times 3. And here I want you to highlight the K squares. I don't know if you remember this from last year, but if all of them have a K squared in them, I can factor it out. I can take it out. I don't know if you remember that. It's the GCF, greatest common factor. Stop talking gibberish, right? But I'm going to say, well, I'm going to take that out of this whole thing. So watch what I'm going to do. It's going to be right at the front, K squared. So we're going to take it out of all of them. Now it's gone in every single of these expressions. So I'm left with 2 times 5 times 2 plus 2 times 5 times 3 plus 2 times 2 times 3. And if you have a different color, this is where something is going to pop out. Okay. Do you notice that this here is exactly the same as this part right here? Compare it. Right? So this here, this part right here, is exactly the same as the original. The original. So what I'm trying to show you here is that the surface area of the new resulting shape, in this case it's a box, but it doesn't matter. It could be a sphere, it could be a cylinder, it could be anything. Of the new one is going to be K squared. So our scale factor squared times the surface area of the original. And here's where we're going to deduct our formula. You're never going to have to do this again, okay? I just want you to see why this is, okay? So we're going to divide both sides by surface area of original. We cancel this out. So what are you left with? Therefore, what's left on this k squared is on its own, right? K squared is equal to surface area of the new divided by surface area of the original. Does this one look familiar to you? If you take away the SA and then you take away the squared. Take your fingers off, Mr. Dixon, I'm copying, right? Does this look familiar to you? The new original? K is new original. Now, what's different? K squared, we're going to have to put a squared there if we're comparing surface areas. So we take it up a notch. Okay? So this one is definitely worth having on your study sheet, and I'm going to highlight the 2 as your exponent, because that's the one that students drop a lot. Yeah. Exactly. Ranveer, you just read my mind. That was going to be my part 2 of this. We can make this exact same formula saying surface area of diagram divided by surface area of original. And I'm going to highlight the square. I honestly think you should do that on your study sheet, because that's what students miss. They get it that it's new original, but when we're dealing with areas, we need to make sure K is squared to get the right answer. And I'll say this again. There are 3 components in this formula. If the question gives you any 2, so if I give you these 2, you can figure out this guy. If they give you the scale factor and let's say the surface area of the original, you can find the surface area of the new, right? So any 2 are given to you, use this formula, solve for it, okay? Next, let's do volume. What do you think volume, if you can make a prediction, what do you think volume is going to look like? What's this going to be? K what? Cubed. Volume of new, volume of original, okay? But sometimes I feel like we need to make sure we understand. So volume of original is simply length times width times height. You can't see it on the screen right now, but it's 5 times 2 times 3. I'm just going to leave it at that. Volume of the new is going to be K5 times K2 times K3. Because remember, in our new shape, every single dimension has been affected by a factor of K. So you see that it's affecting all of them. If you multiply K 3 times, that's K cubed. And we're left with 5 times 2 times 3. And if you have green, I'm just going to show you that this is the same as that. Okay. And I need to make sure this is still saying new. So at our next line is going to be that the volume of new is K cubed times volume of the original. We divide both sides by volume. We're manipulating the formula, right? We want it to look a certain way. That's why I'm doing this part right here that follows. So we cancel these 2. We're left with K cubed, volume of new divided by volume of original. So we're going to go therefore K cubed is volume of new, volume of original. That's formula number 1. Formula number 2 is volume of diagram volume of actual. I made a mistake earlier. I see that now. I'll fix it in a bit. Let's just finish this. K cubed, highlight K cubed. I went diagram original here. You see this? If you just look up for one moment, this is supposed to read actual, right? So let's fix that, or else it may not help you to have original there. So I'm just going to change this to actual. And I'll make a little note in, I'm going to use a red pen for this part. Or some different color if you have it. I will say this up here, note, areas are affected by K squared. Okay? Not just K, K squared. That's the note for areas. Maybe I should give you an example. Example, if K is equal to 3, then K squared is equal to 3 squared, which is 9. So what are you talking about, Mr. Erickson? If the scale factor is 3, if every dimension from one to the other has been, in this case, tripled, then the resulting surface area will actually be 9 times bigger. Okay. There's a K squared relationship between the areas. I'm going to go down to the volume here. Note, volumes are affected by K cubed. Example, if K is equal to, what should I do here? Should I give you a decimal? Because it's not always going to be 3 or 4. Let's do this. If K is equal to 1/2, then K cubed is equal to 1/2 cubed. Do you remember how to, when you have a fraction, the 3 applies to the 1. So 1 to the power of 3 is just 1. 2 to the power of 3, is it 6 or is it 8? It's 8, right? 2 to the power of 3 is 2 times 2 times 2. So it doesn't always have to be an increase. It can be a decrease as well, but the scale factor needs to be cubed for that to work. Okay. We're going to skip a couple pages. Let's go to the top of 34, because you might wonder if you flip through it, what happened. We're going to say skip to 36. So for now, skip to page 36. Okay, 36. If two similar objects are related by a scale factor of 6/7, I made this years ago before 6/7 was a thing, so I must have known, right? So basically saying if the scale factor is 6/7, so what do we know? Let's recap. What does this tell us? Increase or decrease? It's a decrease, right? Let's write it as a decimal as well. I don't want you to forget that. Technically, in this case, you don't need to do this, right? I'm just going above and beyond. So this would be 0.886, or if you multiply that by 100, it would be 85.71%. Review, right? This is just a little review. Okay, decrease. Decrease of what? Which decreased? The original. The original. Original. It always tells you what happens to the original or what happens to the actual. That's what the scale factor tells you. So if this is the original, I don't know, let's just do a cylinder. Okay, if this is the original, then we reduced it. By how much approximately? Just approximately. By how much? 15%. Because the original is 100, this one is 100%, right? The scale factor tells us that this one is 85.71%. So 15% reduction approximately, okay? So this tells you how much remains. So approximately 50% reduction. This is all review. This is technically you didn't have to do all of this to answer what I'm about to do here. But I think it's good to keep in mind, right? So obviously the radius has been affected, right? A smaller radius. The height has been affected by a factor of k. Everything has been reduced. The height has been reduced by the same amount. The radius has been reduced by the same amount. Does that make sense? Right? Okay, so knowing all of that and knowing what we just learned, the areas or surface areas will be affected by what? By k squared. The areas are affected by k squared, not k. Okay? So,
Unity Goodmanson, please head back to room 61 immediately. Unity Goodmanson, head back to room 61 now, please.
so basically it's 6 squared. You know what? You do whatever you need to do here. Some students prefer to do this. 6 divided by 7, so I'm going to go brackets. Bracket 6 divided by 7, close the bracket, go x2, and just get your decimal. I'm fine with that. That would be 0.734 something. I remember I taught you the trick. If you look at my answer key and all of a sudden there's a fraction out of nowhere, I used math, fraction, hit enter, and if it can, it's going to give you a fraction, 36/49. Okay? So you can just state it as 0.73 if that's all I asked you for, you round it there, or 36/49. Okay, so you could have done percentage technically. Technically, you could have done percentage. But the area is different, okay? So the area is not just the scale factor. When I talk areas and I ask you how are the areas affected, how are they related, you need to square. Okay, so I'm going to highlight that. And why? Because we're talking areas. That's why I need to do that, okay? So how are the volumes affected? What do you think? By k cubed. So I take the 6/7 and I cube it. Okay, so you take bracket 6 divided by 7, close bracket. Now I need to use the hat, this hat button for cube. Okay, and that's what you get, 0.734. 2.63, round it, but you could also do math, enter, 216, 343. I prefer this one, especially if I'm going to do some more work with it, but I'm not going to take any marks off if you give me a decimal. Okay. Okay. I want to give you some class time to work, so I will do. Now we're going to get into the nitty-gritty of this unit. Okay. So everything is kind of a variation of this. Okay. An ice cream shop is making a smaller cone for smaller children. Use the diagram to answer the following. Determine the scale factor used to create the smaller cone. We want the scale factor. They're asking us, what is the scale factor? What is K on its own? Okay? What are we using here terminology-wise? Original, and they're making a replica, so this will be new. Okay? So original, new. What do we know of both of these cones? We know the diameter. That is easy. If you have the diameter or just like a linear dimension, it's the easiest way to find your scale factor. So basically, I'm just going to go K is equal to diameter of new divided by diameter of original. Because I know them both, do I need to worry about K squared or K cubed here? Do I need to insert that? Do I need to include that? Because it's not area, it's not volume, it's just something you can measure with a ruler. It's just a length. So here we go. New, 1.77 inches over 2.5 inches. Yay, they cancel out, right? You see that? No need to convert or anything. Cancel them out. I like my fractions. So watch this. You go 1.77 divided by 2.5. Math. Fraction. It's 177 over 250. If it cannot do it, it will give you a decimal. Okay, if it cannot give you a fraction, it will give you a decimal, then that's all we're left with. So this is 177 over 250. I used math 1, to be honest. Math, and then that first option, when you press math, gets you this, okay? If you didn't want that, you can rebel, right? You can be a rebel and be like, nope, I'm going with decimal, whatever floats your boat, you go for it. All right, this is key, this is huge. Once I have my scale factor, it does not change. That's K, K is fixed. So every single thing from here, like this slant, has been affected by K to come over here. The diameter has been affected by K to come over here. Everything has been affected by this, okay? And we know it's a reduction. I don't think that's a surprise to us. Now, how can we use this combined with what we've learned today? Watch. So now we're talking surface area. We don't know what the surface area is of the original cone, but for some reason we do have the surface area of the small cone. See that? For volume, we know how much fits into this cone, but we don't know how much fits into the smaller cone, like how much volume is in there. So that's where a scale factor is going to come in handy. Okay? So here, determine the amount of waffle dough required to make the original cone. Right? We want to know the surface area. Waffle dough is what wraps around it. That's an indication of surface area. So you should be thinking K squared. That's looks like OK squared or something, right? But anyways, that's a thinking bubble, right? That's what you're thinking. So we're going to start with this. K squared is surface area of new, surface area of original. Out of the three, which one do I know? I know my scale factor, correct? I know it's 177 over 250, so I know this. Let's put that in there. 177 over 250. Don't forget to square it. Okay, I'm going to highlight the square. Don't forget to square it. On the other side, I don't know the surface area of the original, but I do know the surface area of the new one, which is 10.15. I'm purposely omitting the units here because somehow the units throw students off. So just put in the number that you know and plug it in there. What would be your first instinct at this point? What should we do here first before we move on? Yes? Square it, yes. We're not going to cross multiply and divide yet because this one is kept hostage by that square. Okay, so let's do that. It's going to get a little ugly, but watch how I do here. I go 177 x2. That gives me 31,329. And then I go 250 x2. That's 62,500. Yes, the numbers get big because you're squaring or cubing sometimes. 1015. And you can go x at this point, right? Instead of surface area of the original. And now you can cross multiply and divide. So cross multiply and divide. So it's 1015 times 62,500 divided by 31,329. You get 20.25. What are my units in, though? The 1015 is in what? Squared inches, right? You see that? So automatically, that's what the units are for. Just trust me on not putting units in here for now. For some reason, that throws students off and they do some wonky stuff. That's it. So I know that my original has a surface area of 20.25 square inches. Okay, keep going. Am I going too fast or what here? Make sure you write it down, yeah. I'm just going to have it on the video or something. I'm not going to actually solve it, but let's say you do not like to work with fractions. You could have gone 177 divided by 250. You get that. And then take that answer and square it. You get that. So this whole thing, instead of a fraction, you would have this. But make sure you don't round. You use all decimals. And then just put a 1 underneath. So you have that decimal over 1. So you cross multiply and divide, you'd get the same answer. Okay, so it's okay to work with decimals. It's not a problem at all. Okay, next. The volume. So we're dealing with volumes. It's once it determines the amount of ice cream the smaller cone can hold, right? If you're filling something, if you want to know how much it can hold, we're talking volume. So it's K cubed, volume of new, volume of original. And that's a terminology I use now because it suits the scenario better, new and original. K is what? 177 over 250. So once you have K, if the question gives it to you, you insert it, we cube it. And which one do I know of these two? I know the volume of the original. So in this case, I know that this is 2454. And my quest is to find how much the new smaller cone can hold. So grab your calculator, so you go 177. I use the hat button and I go cubed. So that's 554, 5233. And then you go 250, hat 3, so you're cubing it. That's 1562, 5 followed by 3 zeros. Is equal to x over 2454. X is, right, a cross multiply and divide. Big numbers, but we've got a big calculator. So.
Excuse the interruption, could I please get a custodian to the office, please?
I like copy paste, so I'm going to multiply by that and divide by that. So I get 8.71. And we are in inches cubed. So if you want full marks, that's what you should get. And it should jive, right? Like this number should be smaller than the volume in the large cone, right? So if you, sometimes students don't put the numbers in the right place and they get a number that doesn't make sense. So you got to watch out for that. Okay. Let me see. I need one more before I let you go. I mean, as in like you work on it yourself for a bit. 38. Next, 38. Coca-Cola has made a new larger pop can. The original is able to hold 355 mLs and requires 322.57 square centimeters of aluminum to produce, while the larger one can hold 500 milliliters. Just so you know, I'm going to write this down. Note, 1 milliliter is the same thing as 1 cubic centimeter. So you can also say this is something that you should know, even for like if you do chem or bio or whatever. 500. You could say 500 cubic centimeters if you see mLs. So this is 355 cubic centimeters. So both of the amount that it can hold are it's essentially a volume. probably worth highlighting. It says A, determine the scale factor. Determine the scale factor. So we don't know what it is. It's a question mark. Determine the scale factor used to create the new can. So because we're talking new, I would call this the original, and this is my new can, right? They have given me enough hints to know that that's what's happening. So question. You kind of have to think K. Can I use the heights of the cans to figure out K? Right, I don't know what the height is here. Can't use that. Can I use their surface areas to figure out K somehow? No. Can you use their volumes? Yes. So I will circle this. I know both of their volumes. Okay. Use to find K. Right? That's the key here to unlock the scale factor. So how does my formula, if I'm going to use volumes, how will my formula start? Like what is going to be what? K cubed. I'm going to go volume of new and volume of original. So this is a variation where you need to find the scale factor. I don't know what K is. That's my unknown. So leave it blank. Just make sure you cube it. Okay. The volume of the new is 500. The volume of the original is 355. What would be your first instinct here to solve for K? You're almost there. What do you do when it's K squared? What would you do to both sides to get rid of the squared? You would square root, right? In this case, you have to cube root both sides. So what we do is, we don't want the cube, so we're going to cube root this side. And we're also going to cube root this side. So you cancel the cube root with the cube. That leaves you with K. And on this side, something that a lot of students miss, okay, make sure you write this down, is that I would like you to think that if there's a fraction that it stays in a bracket, they're invisible brackets, right? So what I like to do is to show my work is I'm going to go 500 divided by 355. I'm going to divide this first. So that's cube root of 1.408 and something. That keeps going. So I need to cube root this thing. Do you remember how to cube root using the calculator? It's a shame that it doesn't have a cube root button. You got to go math, okay? If you don't know where it is, type math, and it's your fourth option. Some of you should probably have that on your study sheet if you need a reminder. So I cube root, I call it, and then I go up to my previous answer, I highlight it, hit enter, enter one more time, and that is your scale factor. I'm going to try to turn this into a fraction if I can. Okay, I'm going to go math, fraction. It can't do it. Right? It can't do it. So just keep your answer like that, and you're good to go. So now you have your scale factor. Now you can solve for the rest. So I'm going to stop here. I'm going to ask you to try pages, so finish 38 all the way to 40. And and I will give you the answer to these two questions that are on this page. So you can, 38 to 40. So the answer to this should be 404.63. And the answer to C is 13.66 centimeters. You're not finding K anymore, guys. K? That's the joke. You're not finding K anymore. You already have it. Now that you have it, if you're talking about the amount of aluminum required to make the larger can, what is it talking about? The amount of aluminum we're talking? Surface area, correct? So this is surface area. I'm just going to get you started here. So what should your formula start with? K squared surface area of, I'm going to go new, over surface area of original. You know K. You know one of these two on the other side. So solve for the missing one. That's what everything is going to be for the next couple of pages. Make sure you start it properly, plug in, and square it if you need to, and then go and solve, cross multiply and divide. Okay, I'm going to walk around.